So in this video, we are going to look into a series RLC circuit, and we would be analyzing and characterizing this circuit by means of a Laplace transform. So we have a voltage source that is x of t, and in the series we have an inductor of 1 Henry, resistor of 3 ohm, capacitor of 1 by 2 farad, and we are having a loop current of y of t. The input considered over here is simply 10 e minus 3t u of t. So we also have initial conditions, that is y of 0 minus, which is 0 ampere, and the first derivative of it is simply minus 5. So in this video we would be calculating the output response, that is y of t, in terms of the zero input response, which is also called as a transient response, or simply a homogeneous solution, that is y naught of t, and the zero state response, that is ys of t, that is the steady state response or a particular solution. So as a first step, let us write the differential equation by means of KVL. And over here I would be plugging in the values of L, R and C. So we would have next differentiating both sides. So we would have a double derivative now, second order differential. Now from the differential property of a unilateral Laplace transform, that is the second differential of y of t, has a Laplace transform, which is s square y of s minus the initial conditions, which are s y of 0 minus and its derivative. So this covers the second differential. Also for the first differential we have simply s y of s minus the initial condition. Now for x of t, d by dt x, so this would have a Laplace transform in terms of s x of s minus the initial condition x of 0 minus. So this can be found from the expression itself, that is, since we have u of t, so anything where t is not positive, so this would be simply 0. Now we are left with sx of s. Again for x of t is 10e minus 3t u of t. So its Laplace transform is 10 1 over s plus 3 with the real part of s greater than minus 3. Also from here, if we are differentiating the input signal, that is d by dt x of t, so in Laplace domain, so this would mean that we would be multiplying with s. So we have 10 times s over s minus 3. So s is multiplied if we are differentiating in the time domain. So now we have all the expressions that we desire. So let us plug all of this into the main differential equation. So from here we have s square y of s minus s y 0 minus the first derivative y 0 minus, and from here we have plus 3s y of s minus 3 y of 0 minus. So this would simply be 2 y of s and this over here is given by this expression, and that would be the 10s over s plus 3. Note that from pair 6, if this is minus, so we have a plus here, so that's why we have plus over here. Now we can combine the ys terms, so then we would have s square plus 3s plus 2y of s. Next we can lump together these initial conditions, so we would have minus y of 0 minus, and we have s plus 3, plus we are left with this, which is y dot of 0 minus, and then we have 10s over s plus 3. So let us bring these two towards the right side, so we would have 10s over s plus 3 plus y 0 minus s plus 3 minus y 0 minus the first derivative. Also we can take the roots of this, and we have s plus 1 times s plus 2 y of s. Now this is our input term, and these two terms are the state terms dependent on the initial conditions. So we have these as initial condition terms. So we can have y of s, and we can bring these two towards the right side, so we would have 10s over s plus 1 s plus 2, and from this equality s plus 3, and similarly we have y of 0 minus s plus 3 minus y 0 minus over s plus 1 and s plus 2. So now we have these two terms. So in the first term we do not have any role of initial conditions, that is, we do not have any role of the initial state. So this is something that we call as zero state response. While the second term, which is over here, this term do not have any role of the input, so we can term this as the zero input response. Or you may call this as a transient response, and this as a steady state response, or maybe as a homogeneous solution, and this is simply a particular solution. So different nomenclatures that you would observe in different textbooks and forums. Now from this equality we will be applying the partial fraction expansion. Which I'm going to do using mupad in Matlab, because any feasible partial fraction expansion can be done easily in the mupad software. So over here we have written the partfrac 10s divided by s plus 1 times s plus 2 times s plus 3, and the partial fraction expansion is with respect to s. So we got these terms with coefficients. Similarly, for the zero input response, y0 is the initial condition, that is y derivative of 0 minus, and then in the denominator we have s plus 1 s plus 2. So over here we have 0 y0 over s plus 1 and y0 over s plus 2. So from here we have y of s equivalent to minus 5 over s plus 1 plus 20 over s plus 2 minus 15 over s plus 3. So we are left with y dot of 0 minus, and from the partial fraction expansion we got s plus 1 and y dot of 0 minus over s plus 2. Now this is simply minus 5 as per the initial conditions. So taking the inverse Laplace transform, so we would have an overall output response of the current, that is loop current y of t, and from pair 6 this would be minus 5 e minus t u of t plus 20 e minus 2t u of t minus 15 e minus 3t plus, so this is now minus, so we have minus 5 e minus t, and this minus will become plus, so we have again 5 e minus 2t. So as this is our zero state response, that is y s of t, and this is our zero input response, that is y naught of t. Note that we can add these two together, so y of t can have a simplified expression, so that would be minus 10 e minus t plus 25 e minus 2t minus 15 e minus 3t. So these two we have already obtained using time domain analysis technique given in our prior video. Now let us visualize the zero input response and zero output response by means of a small simulation. The code is also given in the description of this video. So after initialization, we are setting a time which is starting at 0 and it is terminating at 10. And then we have this zero state response which is expressed over here. And then the zero input response. Then total response, that is the addition of 2. And in figure 1 we are plotting these responses. Now over here, this is our zero state response ys of t. The blue curve is zero input response, so this is y naught of t, and y of t is expressed by this red plot, right, which is a combination of two, or rather an addition of the two.